thank you everyone for being here. I would like to welcome everyone to the first webinar organized by the WCRP Lighthouse activity on explaining and predicting Earth system change. My name is Markus Donat and I'm from ICREA, which is the Catalan Institution for Research and Advanced Studies and the Barcelona Supercomputing Center. And I will be one of the moderators of today's event. Before getting started, we would like to give a short overview of the Lighthouse activity about explaining and predicting Earth system change. So the overarching goal of the Lighthouse activity is to design and take major steps towards the delivery of an integrated capability for quantitative observation, explanation, early warning, and prediction of Earth system change on global and regional timescales, with a focus on the annual-decadal timescales. And the Lighthouse activity is organized around three themes, which are the first working group, which is about the monitoring and modeling of Earth system change. The second one, then integrated attribution and prediction and projection, and the third theme, in assessment of current and future hazards. The webinar series related to this Lighthouse activity aims to provide a discussion forum on topics related to these objectives of the Lighthouse activity and to support the implementation and further development of a scientific agenda that will be taken forward by the Lighthouse activity and partners co-organizing this series. We are currently planning to have these events on a bi-monthly basis, so every 2 months. The webinar today has a focus on record-breaking extreme events, and we will hear presentations that will cover the global analysis of the occurrence of record-breaking extremes and examples of such events in South America and Asia. Before we get started now, we also want to do a bit of advertising. These topics, among many others, will also be fully explored at the WCRP Open Science Conference that will take place in Kigali, Rwanda in October next year, 2023. And the scientific organizing committee is working hard on an exciting program for the scientific community, but also for users of climate information. And for more details and to register your interest to receive further information about the conference, visit this website, please. We hope to see you all there. And now I pass on to our other moderator today, Matilde Rusticucci.
Thank you, Markus. Good morning, good evening, good night to everybody. Thank you for participating in this activity. I am Matilde Rusticucci from University of Buenos Aires. Before I introduce our first speaker, I'll provide an overview of today's events and modes for interaction. Our three speakers will present before the Q&A session. However, during their talks, feel free to pose questions and indicate to whom your questions is directed to using the Q&A feature at the bottom of the Zoom window. And everyone can upvote the question posted there. Please reserve the chat function for technical issues related to the webinar and use the Q&A for questions to the presenters. We will then get to this question in a discussion session following the presentations. We also have a number of experts in the audience, so we want to encourage a lot of interaction. For the presenters, we will give you a warning when 5 minutes are left and when 1 minute is left for you to wrap up. Now, it's my pleasure to introduce our first speaker, Dr. Eric Fischer. Eric Fischer is a senior scientist and lecturer at ETH Zurich, Switzerland. In 2007, he completed his PhD at the Institute for Atmospheric and Climate Science at ETH Zurich. He then worked as a postdoc at the National Center for Atmospheric Research, NCAR in Boulder, Colorado, and as a visiting scientist at the University of Reading, UK, before moving back to ETH Zurich. He's a lead author of the IPCC AR6 assessment report and is a co-lead of the WCRP Grand Challenge on Weather and Climate Extremes. His research interests include understanding and quantifying changes in weather and climate extremes in a warming climate, climate model evaluation, detection and attribution of observed changes, changes in climate variability, quantifying and constraining uncertainties in global to regional model projection, heat stress in urban environment, and the climate response to volcanic eruptions. Thank you, Eric, for being here, and the floor is yours.
Thank you very much, Matilda. Thank you very much, Marcus, for inviting me. It's a great pleasure to open today's webinar with a presentation, which you can hopefully see now. I'm going to talk about understanding and quantifying very rare and record-shattering extremes. This is work I've been doing together with colleagues at ETH Zurich, NCAR, Cornell, and many others involved, some of them listed here. So the reason why we have been focusing on these events, these type of extremes that break previous records by large margins, is because we think it's typically the first occurrence of these type of extremes when the impacts are largest. And then after it once occurred, you see a lot of action, investment in flood protection, warning systems, and so on, so that hopefully the second time such an event reoccurs later on, the impacts are sometimes smaller. So we were often asked by practitioners about information of what the worst possible case there is that they should be preparing for. We had such question in terms of flooding by the Nuclear Safety Inspectorate for nuclear power plants, but here we're looking at a much simpler case. We're looking at temperature. What I'm showing you here is a time series coming from a climate model. From a large ensemble, I picked one specific one. You're going to see why in a minute. And what you're looking at is the annual 7-day temperature maxima. In other words, the warmest week per year over an area, average central US in the NCAR Community Earth System model. We have a lot more data than we typically have. 170 years is much more than we typically have in terms of observations at daily scale. There's also a little trend, which is actually the case for this particular region, even in observations. So let's assume we were asked here what the highest possible event is that we should be expecting to see in the years to come. The good thing is that for temperature, the extreme value distribution is typically bounded. And we understand why. There are physical processes that constrain peak temperatures. There's good reasons why we've never seen 60, 70 degrees 2-meter temperature anywhere on the planet, right? Because radiation on the cloud-free skies sort of puts a limit. You could completely dry out the soil. And at some point, the Planck feedback, sigma T to the force, becomes so strong that you basically have such a limit. Also very interesting literature arguing that for any given temperature aloft, for instance, at 500 hectopascal, there's also a limit on how much you can actually warm the surface until you actually trigger convection. This is a very nice preprint that is currently reviewed by Ying Zhang, where I'm not involved, but I think it's a very interesting aspect. So we have such a limit, and then you could argue, well, if there is no trend or not much of a trend, then we could be very naive and fit the GV to assume a stationary climate. You can actually even do a non-stationary fit, which we also did in our paper, and still you don't see much of a change. So you could argue, well, is this a good estimate of what is coming to follow? Well, it's not, because I'm showing you what in this particular simulation follows a couple of years later, and I have to adjust the scale. We do find an event that goes way, way beyond anything that has been previously simulated, right? We call this a record shattering. Other people call it record smashing extreme. So 5 standard deviations. And I could tell you the first time I saw this in my time series, I thought, okay, there's a glitch in the post-processing of the data. The more we looked into it, we started to understand, at least in a model context, it looks like a reasonable event. Whether it's true for the reality is another question. But there's a temperature anomaly, there's an anticyclone where we would expect it, right? We do actually see diabatic heating that increases potential temperature going in the block. Then we see subsidence, a very efficient adiabatic heat engine through subsidence. And then plus on top, we have a very, very dry soils. So we have a low evaporative fraction. So the well-known ingredients of a heat wave, but just in an exceptionally anomalous combination, right? Nevertheless, we still had a hard time, I can tell you, to get this through review because people thought, okay, this is possible, but it seems to be so unlikely. So then we argued, well, if it is unlikely to see it at some spot, but to see it somewhere on the Northern Hemisphere is actually a considerable probability. And it was a pure coincidence at the time when the paper appeared, the 2021 Pacific Northwest heat wave happened, which was exactly the type of event we've been talking about, which basically exceeded the previous record by 5 and more degrees in some cases, right? So we had a very easy time then to communicate the result and say, look, this is exactly the type of event we've been thinking about. And we had previous events, slightly different timescales, which we already described in the paper, the 2020 Siberian heat anomaly, the 2003 summer heat wave in Europe, the angriest summer in Australia. People still told us, okay, you've been just lucky in terms of communication. But honestly, this year I could have basically taken any week. We've seen spikes like this in Antarctica in March, other more seasonal records in Sacramento only a couple of weeks ago. We've seen record breaking and actually smashing behavior in alpine glacier melt rates and also in Greenland melt events recently. So how come do we see these type of events? Because we need to remember that the longer we observe, the record should actually become rarer and rarer, right? The longer you basically observe and measure, the less unseen you should expect to see, obviously without climate change. An analogy I'm often using is long jumping world record with talking to the public. The world record in long jumping dates back from the 60s and was only marginally exceeded in the 90s and has been standing ever since. So if an athlete would come now after so many students at high schools and everyone tried it to do long jumping, right, and suddenly beat the standing record by half a meter or a meter, that would be very suspicious and the person must be doped, right? So how come that we currently see this type of records to occur? Obviously, because we're not in a stationary climate, right? But still, we see so many going on. This is a visualization that Bloomberg is based on our paper, and the actually same picture for 2018 looks even more dramatic. And you could draw this again for 22. You see record behavior and record smashing behavior all across the planet. So in our paper, we revisited a very nice analytical approach solution put forward by Stefan Rahmstorff and Dim Kumu a decade ago, where I've been saying the probability of record is declining with 1/n if there is no change, right? Very simple statistic, actually independent of the distribution. But if we have a linear trend, this is obviously no longer the case. We adapted the solution and said we can also derive this for any type of underlying forced response, any nonlinear time-varying response, and any record margin. So we were arguing the probability of shattering a record in any given year is a product of the probability that a given record is not previously exceeded. And you could think, obviously, this declines over time. Particularly if you're in a warming climate, this rapidly declines. So this probability, which is constantly declining, times the probability of then exceeding that given record by a record margin C in that given year, right? So once we work this out, we've been arguing, well, now we can actually check whether we can explain the behavior that we see in our large ensemble. So you're looking here at still fully coupled model results. To the left, you see a very dramatic forced response, averaging 84 members of the NCAR community Earth system model. We also looked at many other large ensemble, CMIP 5, CMIP 6, by the way, but what you're looking at here is coming from that. We hit the system hard to get good understanding. And to the right, you see actually the probability of breaking a previous record in the corresponding simulation by 1 standard deviation. We lowered the bar to get better statistics. And what you see here is the probability is increasing. We're starting off very low because the simulation already started in 1850, and after 100 years, it is almost zero probability to break the previous record by 1 standard deviation. Once the warming picks up, it goes up. So we've been prescribing the warming profile to the left in our analytical solution and see whether we can actually reproduce in a time series model what we see here. That's shown as the dotted line to the right, where you see actually we come reasonably close to what the fully coupled model shows, slightly underestimate the behavior. We then realized that in this particular realization, the variance, so the year-to-year variability in summer, also somewhat increases. So if we further account for that in our time series model, we come remarkably close. And at that point, we thought, okay, this is really cool, because now we can actually simply look at our time series model and look, for instance, what would happen if we had a linear warming? Well, the probability of shattering the record would be constant. If we had no warming, the probability would be nearly zero. If we have much quicker warming, the probability would go up, particularly after a period of no warming, right? What's interesting is the higher the rate of warming, the higher that constant probability. And once we were able to stabilize in a new warming, be that 2 degree or 3 degree, we would still see a lot more events going on, but the probability of record would go down again. Because once we spend enough time in a warmer climate, we would expect to see less and less and less of these records to occur. So the impact would still be there, but the notion of record behavior would no longer be that prominent. So we concluded in our paper that record shattering extreme depend on the warming rate and not only the warming level here, unlike many other characteristics of the traditional way of looking at extremes that scale with the level of global warming. So we've then also been wondering, isn't it frustrating that we always only act after these events occur? We've been wondering, can we foresee these type of events? And I'm talking not about predictability here, about if the province of British Columbia, the state of Washington, had asked us back in 2020, could we have told them that in the event 5 degrees warmer, what they've seen is possible? So what we could have done is we could have run climate model already back at that time and see whether they can reproduce the behavior of that era 5 anomaly. And so we did. We ran 30 members from CSM2 here, which you see the dashed lines here, different events from different years that come reasonably close. We thought if we want to ask the question whether things could turn out even worse, because of that bounded nature of the GE, we would need to run many, many, many more ensemble members, which simply is no longer affordable. So we wanted to be cleverer than that. And we introduced a new approach in which we take the climate model, take one of the worst case event C that you've just been seen before, and to reinitialize, like in a forecasting mode, the model by perturbing only by a round-off perturbation. So we only changed basically a couple of bits in the atmospheric initial conditions so that each of the trajectory is as alternative realization, and we nearly conserve energy, mass, and momentum here. If you see, we run 100 members and none of them actually gets the event again, which may be not surprising because we've been looking at a very, very extreme event. But it turns out that we were just unlucky. If we start later, a couple of days later, and do the same experiment, actually we can go and find realizations that go way beyond. So it turns out that with this very simple approach that we know from numerical weather prediction, but we use a tiny perturbation, we can actually efficiently produce storylines, time series for these type of events and sample very, very extreme cases and start to understand the processes. So for all the dashed lines you've seen before, we actually were able to produce events that go way, way beyond, that actually now also go way beyond what the Pacific Northwest heat wave looked like.
5 minutes left.
Okay, thank you. The interesting thing is that we can even look at the processes and try to understand what limits those anomaly in these cases. So we only picked the event based on the 5-day maximum temperature anomaly over the Pacific Northwest. Nevertheless, it turns out that our events look very similar even in the spatial pattern of temperature, in the spatial pattern of Z500 anticyclone. If you plot the whole northern hemisphere, you see a typical Rossby wave pattern. In some cases, we have a preconditioning soil moisture anomaly, in others less. So we can actually go in and study processes here. So I'm concluding here that climate models could have been used to foresee the potential intensity of this type of event. So we could have drawn these dots that you see here already back in 2020. An interesting question is if anyone would have believed us. Would you believe those dots, which you haven't seen, where we look at the black at era 5, and I'm arguing these dots, according to our ensemble boosting approach, are suggested by the climate models, right? That's an interesting question, and we've been thinking about this now for a while, and I'm arguing that building confidence here is really going through process understanding. And that's where I think your Lighthouse activity here that you have is so essential, because ultimately we can only build confidence in storylines of the prediction and a projection of unprecedented extremes by process understanding. We need to go in, ask the question, do these processes look realistic or not? And then basically we can move forward. An interesting aspect is also there are different methods, and I'm really arguing as a community, we should address similar question with alternative approaches. People have been suggested that have been using successfully initialized hindcast on weekly to decadal timescale, the Unseen project from the UK Met Office and colleagues and partners. We could be looking at analogs in space. There has been these very dramatic heavy rainfall event in the middle of nowhere in northern Italy last year, and one could ask the question, could the same event have happened over the city of Genoa? It would have triggered an enormous disaster. We could look at analogs in space. How would a historical event turn out today by prescribing the upper air winds, changing the SSTs, running a case like Tales of Future Weather with initialized forecasts, or building process-based qualitative storylines. So I think we need to prepare as a society for events of unprecedented intensity. This is also one of the summaries for policymaker statements we have in AR6. The probability of these type events of record-shattering extremes depend on a warming rate, and we are currently in a period where the forced response is actually showing a very strong warming rate. Ensemble boosting is one way of looking at that, but what we need is alternative approaches, different lines of evidence to build confidence. And ultimately, to build confidence, this requires process understanding. I think this Lighthouse activity can play a very important role in this. Thank you very much.
Thank you, Erich. If anyone has questions for Erich, please post them in the Q&A box that you probably find on the bottom of your Zoom app window. And we will address all these comments, all these questions also during the discussion session following the last speaker. Now, it is my pleasure to introduce our second speaker, Dr. Maria Laura Bertolli. Maria Laura is a senior scientist and professor at the Department of Atmospheric and Ocean Sciences at the University of Buenos Aires in Argentina. In 2007, she completed her PhD at the University of Buenos Aires and has been working since then at the university. Her research interests include the understanding and modeling of climate extremes, regional climate modeling and statistical downscaling, synoptic climatology, climate variability and change and their impacts on socioeconomic activities. She is the lead investigator of the Cordex flagship pilot study in South America, extreme precipitation events in southeastern South America, a proposal for better understanding and modeling. And she is a Cordex contact point and WCRP regional focal point for South America. Maria Laura, thank you for being here. The floor is yours.
Okay, thank you, Marcos, and thank you for the invitation. I will share my screen now. Okay. Okay, can you see my presentation?
Yes.
Okay, great. Good morning, everyone. My name is Maria Laura Bertolli. I work at the University of Buenos Aires in Argentina, and I will talk about record extreme precipitation in southeastern South America, in a specific region in South America. And why the southeastern South America? I took this image from a forum, a WCRP forum that was held last year, a virtual forum. And I like this image because it shows several aspects of South America. One of them is the uneven distribution of the population in South America. Here you can see Buenos Aires, the city where I live. You can see here Sao Paulo in Brazil, and many other large cities in South America, like here, for instance, we have Asunción in Paraguay or Montevideo in Uruguay. So, and this region here is southeastern South America. Southeastern South America is a very populated region with large urban settlements. And if we take a look at another aspect of South America, I'm here showing you the extreme precipitation, the 95% of daily precipitation in South America. And you can see here this large area that is southeastern South America, that it is a hotspot for extreme precipitation event. It is a large area that encompasses many countries. These extreme precipitation events are associated with severe weather. This is the seasonal distribution of annual flash density. And this black box here is southeastern South America. And as you can see, this black box here is all year long red. That means that the lighting activity is presented all year long in this region. Another aspect, for instance, of southeastern South America is the occurrence of compound extremes. This is the mean annual frequency of sequential compounds of dry spells and extreme rainfall. And you can see that southeastern South America is the scene of this kind of extreme compounds. Southeastern South America is a highly populated region with large urban settlements that are exposed to extreme precipitation events. These extreme events are typical features associated to deep convective storms, sometimes organized as mesoscale convective systems, with a very severe weather with a large hail and lightning and sometimes tornadoes. They are becoming more frequent and more intense, and they have large socioeconomic and hydrological impact. And although we have studied these extreme events a lot, and much work has been done to understand them, it is still a challenge to better identify the factors, mechanisms that determine their location, intensity, and frequency, and also their large impact. So how do we address the study of these very extreme events? Well, due to the relevance of these events and considering the magnitude, impacts, and the area of influence, it is essential to address their study with coordinated science and with interinstitutional collaboration and networking. There have been many initiatives that address the study of the extreme precipitation events in the region. One of them is the Cortex flagship pilot study that is an initiative that is endorsed by Cortex. And this initiative has these objectives: to study multi-scale processes and interaction that result in extreme precipitation events, and to develop actionable climate information from statistical and dynamical downscaling based on co-production with the impact community, with the impact and user community. I am the lead investigator of this initiative, so I am representing here a large group of people that is working hard on this. Well, in the framework of this initiative, we identified the 2009-2010 warm season that goes from October to March as a record season in terms of extreme precipitation. And you can see here the time series of the areal mean frequency of precipitation events. This is the time series, and we identified this season, 2009-2010, as a season with a large number of extreme events. If we take a closer look within that season, this is the time series, daily time series of maximum daily precipitation in Southeastern South America station data. And we can see here that all days within that season registered precipitation in at least one weather station, except for 2 days, this one and this one. That means that all days rain somewhere in Southeastern South America in that season. And not only it rains all day, but also it rains with a large, very, very large amount. We have we are here the 99th percentile of daily precipitation, that is around 90 millimeters per day. And you can see that the daily precipitation in Southeastern South America exceeded that percentile many, many times, and exceeded it very with intensities that were really exceptional. To have an idea, the 150 millimeters per day is here, and that value was exceeded many times too. This warm season was record in terms of seasonal, in terms of 3 aspects. One was the total seasonal precipitation amount, that in this map we can see that the total seasonal precipitation amount exceeded the 95th percentile for the seasonal precipitation in a large region that is the red dots here. It was a record season in terms of the number of extreme events. We have many extreme events, but also in terms of the intensity of this extreme precipitation. So we chose this season, we studied this season, and we also selected 3 specific events that are indicated here. These events are these ones, because these events have also a large aerial extension and different aerial extension in their maxima. And the maxima is located in different parts of South America, of Southeastern South America. I will show some results of this event, that is the event 3. This season was a record season in terms of precipitation, but also in terms of the impact of the precipitation. This is the Uruguay River basin that is located in Southeastern South America. The Uruguay River is shared by 4 countries, Brazil, Paraguay, Argentina, and Uruguay. This river is very important for the region because of the hydroelectric power utilities which supply energy for the region and also water for consumption. And the navigation along the river is also very important for the integration of the regional economy. So if we take a look at the stream flow of this river, we found that in November 2009, it's a very extreme event for the stream flow. In this month, the stream flow remained 29 days above the 95 percentile and 14 days above the 99 percentile. So this season was a very extreme season in terms of precipitation and also in terms of the impact. So how did we study this record season? In the framework of this initiative, we coordinate an experiment to simulate the complete season using statistical downscaling models and dynamical downscaling models, including convection permitting simulations. These simulations were used as input for 2 impact models. One was the hydrological model, and the other was the crop model. I will show this part only, but we wanted to analyze the study to analyze the impact of these extreme events on 2 main productive systems in Southeastern South America. Well, I will show you some results. How did the different observational data set capture the precipitation stream? Well, we can see here different observational data sets for the total precipitation season, and this is the same figure as this one, but with another perspective. And we can see that most observational data sets present a similar spatial structure, but with different intensities and with different aerial extension in the maximum. This is very well shown here, that when we have here these 2 data sets that are very, very extreme. If we now take a look at the event number 3 in November 2009, we can see almost similar characteristics as before. The intensity of the extremes is very variable among the observational data set, but also the aerial extension of the precipitation events. Additionally, in these particular events, the spatial structure is also very variable among the different observational data. So this shows that the observational uncertainty in this region is very large concerning the extremes. Now, how did the different models simulate the precipitation extremes? Well, we have here the simulations that we performed, some of them. These are dynamical simulations, these are statistical simulations. And well, this was quite challenging for the observations. So it was also quite challenging for the model, but the model did a good job. Most simulations were able to represent the spatial gradient of the observed precipitation. Not all of them, but most of them. The maxima was misplaced in some cases, and the spatial extension of the maxima is very variable in the model. If we take a look at this kind of figure, this is to show that the spread that we saw in the simulations in the previous figure, this spread in simulations is similar to the spread that we have in the observation. This is the simulations for the event number 3 in November 2009. We have different dynamical simulations, statistical simulations. We can see that most models are able to reproduce a maximum precipitation, but with different intensities and with different locations. But again, this spread in the simulations that are these
5 minutes left
here, okay, are within the observational answer time. We also analyze the timing of the precipitation. This is the aerial average daily precipitation during the complete season. In black, we have the stations. In blue, we have the ensemble of statistical simulations, and in yellow, the ensemble of dynamical simulation. And we can see that there is a very good agreement between the sample mean of simulations, indicated that both models are able to reproduce the correct timing of precipitation occurrence. That it was a challenge identified at the beginning. But the exact location and intensity are still a challenge, as we saw in the previous figure. We also analyzed if the models were able to simulate the synoptic driver associated with extreme precipitation. These are these ingredients that are present in this extreme precipitation: the South American low-level jet, the middle and upper flow, and the low-pressure system leeward to the Andes here are very important for the developing of these extreme events. Here we can see some simulations of precipitation at 6 hourly accumulated precipitation, and where and how the model locate them. Okay, but I will focus on the synoptic drivers. This is ERA interim as a reference data set, and these are some of the simulations with convection and non-convection permitting. And we can see that all simulations are able to capture the mechanisms that favor deep convection, that are the low pressure system leeward to the Andes, and also the strengthening of the low level jet here and here, and also the moisture flux convergence that is indicated with this line, black line here. This vertically integrated moisture flux conversion is associated with the location of the maximum precipitation. So it is identified as a footprint for moist convection. The discrepancies among members are found in the location of the synoptic patterns, which lead to discrepancies in the flux convergence of moisture, and then, of course, in the simulated precipitation pattern. And the last figure that I wanted to show, this is an analysis in progress regarding the stream flow in the Uruguay River Basin. These are all simulations of the stream flow. This part here is simulations using as input dynamical simulations, and these are simulation of the stream flow using as input the statistical simulation. And well, we can see what here that there is an interesting spread in simulations, but with very good correlation between them. The three extreme events in precipitation that we identify in this season are clearly seen here in the spring. Well, the take-home messages from this experience is that precipitation measurement is a major challenge in South America. The observational uncertainties are very large, and in situ observations are very valuable for this kind of studies. We identify strengths and weaknesses of simulations, but we no model, but there is no single model that performs best. So all this evidence, we need to produce ensemble of simulations and multimeter to understand the processes involved in these extreme precipitation events and their impact. Interinstitutional collaboration and coordinated science are key aspects to address this kind of stuff. Thank you.
Thank you, Maria Laura. As before, if anyone has questions for Maria Laura, please post them in the Q&A box, and we will address them during the discussion session following the last speaker, which is the next one. And it is now my pleasure to introduce Dr. Tianjun Zhou, who is a senior research scientist in the Institute of Atmospheric Physics at the Chinese Academy of Sciences, and adjunct professor in the University of Chinese Academy of Sciences. He works on climate modeling and climate dynamics with focus on monsoon variability, climate extremes, and how the global monsoon system responds to anthropogenic and natural forcing agents. He was named to the prestigious highly cited research list from Clarivate Analytics for Geoscience in 2018-2021. He served as the lead author on the 5th and 6th assessment reports by the Working Group 1 on Intergovernmental Panel of Climate Change, IPCC. He's a member of the World Climate Research Program, Working Group on Coupled Modeling, WGCM, and co-chair of CMIP6 Coupled Model Intercomparison Project Phase 6, Global Monsoon Model Intercomparison Project, GMMIP. Tianjun, the floor is yours.
Thanks to Mathilde. Let me share the screen. Hello, everybody. It's my honor to talk about the record-breaking extreme events over Asia from the perspective of attribution and projections. For Asian, the first imagination is that we have a large populations. For climate, we know East Asia, actually the whole Asian area is dominated by monsoons. We know both anthropogenic forcing and the internal variability, such as El Nino, can affect monsoon activity. This kind of effect can result in a strong impact of climate extremes. You know, there are many kinds of extremes. Today, I will first talk about the attribution of the record-breaking heat extremes. I will show 3 examples. The first case is for the record-breaking heat wave of 2013 over eastern part of China. And here is the number of heat wave days. You can find it lasted nearly 2 months. And here is the stations where there is record breaking. You can find it covers a large area. To do event attribution, we need numerical model results. We have 2 sets of simulations. The first is EGCM forced by both anthropogenic and natural forcings. The second set of simulation is only forced by natural forcing. We have ensemble members of 50. We also use the probability ratio to estimate the anthropogenic forcing. We first calculate the probability of the event occurring in the natural forcing run, and then we calculate the probability of the event occurring in the all-forcing run. And finally, we can calculate the probability ratio, which is the factor by which the probability of the event has changed under anthropogenic forcing. First, how about the observations? You can find the high temperature or eastern part of China is dominated by high pressure system. And here is the result of ensemble mean of the models. You can find the observational features can be reproduced. This suggests the observed change is a forced signal. We can also estimate the probability density functions in the all-forcing and the natural forcing. If we can compare the red line with the green line, you can find the anthropogenic forcing has increased the probability of such kind of event. We show the probability ratio here, you can find is about 18. So while both natural variability and the anthropogenic forcing have contributed to the observed heat extreme, it's evident that the anthropogenic forcing has increased the chance of the heat wave occurrence observed in this year. The second case is for the record-breaking heat wave over the Northeast Asia in the summer of 2018. And here is a special pattern of the extreme temperature. You can find it affected a wide area, including Northeast China, Korea Peninsula, and also Japan. What I show here is the time evolution of this record. You can find the heat wave lasted almost 1 month. The heat wave also displayed a record-breaking intensity.
Apologies, we seem to have lost connection with Tianjun. Tianjun, can you hear us?
Okay, maybe I can try to call him.
Yes, please, if possible, please, Tianjun.
He got an internet problem, so wait a little bit, he will rejoin.
Okay.
Okay.
While we are waiting, if Marcus or Mathilde, would you like to address one of the questions? So Eric or Maria Laura can respond to that. What do you think?
Yeah, let's use the time for maybe a specific question on some of the talks, then we can have the more general discussion also when Tianjun is back.
Yes.
Maybe shall we start with there's a question to Eric. If we can attribute a cause of such a record event through process-based studies you mentioned in the outlook.
I'm sorry, Marcus, I think Tianjun is back here.
Perfect. Okay.
Let's see if he can hear us. Tianjun? Okay, he's sharing a screen now, so I guess he's able to hear us.
We get back to this one later.
Tianjun, can you hear us?
There's no
I think we can hear us, Tianjun, but not good enough.
the slide to okay.
It's intermittent. Can you repeat it, please? We can't really hear you much. Oh, we do see your screen now. Just for information, Tianjun, we are not able to hear you.
Maybe better if we can have 1 or 2 questions, because the internet, I know the internet will be 1 or 2 minutes delay. So after 1 or 2 minutes, it will be better for Tianjun.
Okay. Tianjun, just let us know when you think the connection is better and you'll be able to talk again. Marcus, would you like to continue with the question?
So let's maybe have a question to Eric and the question to Maria Laura. So, the question to you was basically, can we attribute the cause of such a record event to process-based studies that you mentioned in your outlook? And if so, do you suggest any specific statistical approach?
Yes, thanks. Very good question. So, you know, particularly in these very, very extreme cases, it's often a nonlinear interaction between many, many processes. So attributing to individual causes is usually quite challenging. But when you're thinking of this, I mean, there's different ways of addressing this question. So one could do it statistically. So we tried this by using general extreme value theory and using different process-based covariates, right? So you, rather than only using global mean temperature, you could also use anticyclone intensity, anomaly, something like that, as a statistical explaining variable or predictor. I think more promising is to disentangle it in model experiments here, the attribution question. And I think we could do that. So we could take this model and disentangle the event, take the atmospheric circulation, prescribe it, and change the sea surface temperature. So there's very nice papers by a lot of people who tried this, and I think come up with very promising results. There's also the idea of, for instance, if you use the UK unseen approach, which is a basic initialized forecast, to use more initialized forecasting systems to do address the attribution question. So you'd be changing the SST and then look how the event and how the probability and the intensity of these type of events would have evolved in a different climate state. There could even be a future state possibly. And I think this is very promising because with the forecasting system, we have good understanding about the forecast skill. They're typically high resolution. So I think that will be a very promising way forward.
Okay, thank you. We have a question for Maria Laura. Maria Laura, okay, thanks for your interesting talk. He says, what do you consider to be the main learnings from the Cordex flagship pilot study in terms of improving regional climate prediction and attribution capabilities?
Okay, thank you. Well, I think the main learnings are designing the experiments based on co-production, involving the end users of our simulations from the very beginning in the designing of the experiment, because we sometimes are very focused on some specific aspects of extremes that we miss what they need for their impact studies. I think that's the main learning. Other learnings are to work in a networking that I emphasize this a lot, the interinstitutional collaboration, especially in regions such as South America. It's very, very important to address this kind of study, not only to share resources, but also to share for instance, data. The data availability is not that easy here, so it is a big effort to get the data for this kind of studies.
Thank you. Marcus, do you want to? We have a question to Eric.
I think Tianjun looks to be back.
Yeah.
Okay.
See if we can hear him, and then we can continue the presentation.
Tianjun, we can see your screen actually. We're not sure if we can hear you though. So, okay, I think so.
We cannot hear you. At least I cannot.
No, we can't.
Hi, Tianjun, we can't hear you.
This is unfortunate and shows the challenges of such a global webinar.
Marcus, maybe another thing the conference department is proposing is that I share the screen so that it consumes less data for him, and maybe he can just talk. I'm not sure if Tianjun is able to hear us. Could you respond in the chat, Tianjun, if you can hear us? I can share the screen, the presentation for you.
I think he's mute.
Not from our side. It doesn't seem to be muted. Unless he has some audio issues. So I'm going to share the screen for his presentation. So to see if he is able to get the connection.
Okay.
Yeah, let's see.
依然
okay.
是我用你的话筒，然后我用这个我来显示屏幕是吧？OK， 好。
Okay, I think Tianjun will use my my mic, and let's try.
Okay, so
Okay, thanks to Li Jing. Yeah, this is a choice. Here we estimate the contribution of dynamical and thermodynamical contributions.
Okay, I'm not sure if we see the presentation. Just a minute. Yes, we do. Okay, that's perfect. Thank you. Proceed. Yeah, carry on. Sorry.
So now can you hear me now? And you can find the contribution of the dynamical component is less than 20%, while the contribution of the thermodynamical computation is more than 800. What percent? 80%. The implication of this is that the probability of the 2018-like record-breaking heat event will increase in the future associated with global warming. This is also the longest heat wave in South Asia. So Dr. Mi from South Korea has also studied this event. They have used two sets of simulations. You can find the difference in the estimate of probability ratio. However, at least human activities have quadrupled the probability. This is the case for case 2. For the third case is the heat wave in India of this year. Here is the result of observation. You can find much of this year was the hottest in India over the past 122 years. In Delhi, the observation is nearly 50 degrees, 49 degrees Celsius. And here is the result of the attribution from World Weather Attribution. This one is the multi-model attribution of the probability ratio of the heat wave due to historical warming. You can find climate change has made this heat nearly 30 times more likely. They also made projections under two warmers future, and they found the change in the probability will be with a risk ratio of 8. And also there would be an additional increase in the intensity of 1 degree. How about precipitation? I will also show 3 cases. The first case is the record-breaking floods in China occurred in 2020. The Yangtze River Valley here was the rainfall during the June and July was the highest on record since 1961. The direct economic loss is more than $20 billion US. So here is the observation of the mean stage for the anomalies. You can find the rainfall this year is 2 times of climatology. And here is extreme index of RX28D. You can find this count of persistent heavy rainfall was about 94% stronger than the climatology. And also it breaks the observational record since 1960. So we use the CMF6 detection and attribution model results to estimate the contribution of greenhouse gases and aerosol. And here is the PDF of the extreme index for the greenhouse gases forcing rate. You can find the greenhouse gases forcing actually had increased the probability of such kind of event by about 44%. This is due to the wetting atmosphere associated with greenhouse gases forcing. And here is the PDF of extreme index for the aerosol forcing. You can find the aerosol forcing has decreased the probability by about 73%. So the net effect is that the anthropogenic forcing has decreased the probability of such kind of event. The second case is for the persistent heavy rainfall occurred in central western China in the summer of 2018. The anomaly is nearly 2 times of the climatology. This is the time evolution of the 4-week persistent index. In the observation is once in 6-year event in the observations is also record breaking. So again, we use models to estimate, to do the event attribution. Here is the PDF of RX1D for all forcing and natural forcing. You can find for the RX1D, we observe increased daily precipitation extremes due to the warm, wetting atmosphere. However, if for the RX28D, you can find decreased persistent rainfall extremes. This due to the aerosol forcing. Due to the aerosol forcing, we found weakened monsoon circulation here. So over the East Asian domain, aerosol is very important in forcing the extremes. The third case is for this year, Pakistan flooding. Based on the report, the flood water has covered nearly 1/3 of the country and affected more than 2 million people. The effect of this flooding is more evident if you compare the satellite image in May 22nd and also the August. Again, here is the result for the world weather attribution. Here is the observed 5-day rainfall, and here is the intensity change of this count of once in 100-year 5-day rainfall due to historical warming. Actually, based on the estimate, the 5-day maximum rainfall over this area is now about 75% more intense than the natural run. And here is the estimate under 2 degrees of warming. The rainfall intensity will increase further for the 5-day event under 2 degrees warmer future. That's the case for the attribution of both heat waves and also extreme precipitation. How about the projection? I also show some examples. The first is the case for heat waves over East Asian domain. You know, there are many indices. Here, what we use is TNX 3-day, which is the highest 3-day mean daily minimum temperature in a year. And here is the difference of the extreme index between 2 and 1.5 degree scenario. You can find also for global average, the difference is only half a degree, but over East Asian domain, the extreme index is more than half a degree. And here is the land fraction in East Asia, where the historical record is broken in the future. You can find there will be an increasing coverage of the record-breaking heat extremes over the East Asia. We can also estimate the avoided impact of half-degree less warming for many counts of extreme indices. We show the result over Mongolia, East Asia, Korea, Japan, and other small domains. Please skip the details. The final conclusion is that the half-degree lower warming will avoid about 40% of the increase in heat extremes in terms of intensity, frequency, and duration over the East Asian domain. How about the extreme rainfall? Here, we show observed once in 20-year extreme index under a warming of 1.5, 2, 3, and 4 degrees. You can find the current day once in 20-year event will be once in 15-year event under 2 degrees global warming, and nearly 1 10-year event under 4 degrees of warming. So this suggests we will have more frequent extreme rainfall under warming conditions. We can also estimate the avoided impact of half-degree less warming. And here is the avoided impact of the land and the population exposure to once in 20-year and once in 10-year extreme rainfall. Here is the case for South Asia. You can find the half a degree less warming will reduce the area and the population exposure to once in 20-year or once in 10-year events by at least 20 to 40% in the South Asian domain. In addition to the mean state and the extreme rainfall change, another part of the precipitation change is the variability. What I'm showing here is the increased variability of precipitation across time scales from daily to monthly, interseasonal, and interannual at the long term. In the projection, you can find nearly 2/3 of the land on Earth will face a wet, get more variable climate on daily to multi-year timescales. What's the implication of this? This count of response suggests we will have wider swings between dry and wet extremes in the future. So to make a summary of all this evidence, there is high consensus that for the attributions, we can detect as projective influence on the occurrence of record-breaking extremes. For the projection, there are also green evidence for the increasing threat of the unprecedented events in the long term. But for policymakers, one question they concern is how about the reliable near-term prediction? Because they need this kind of information to support both climate change adaptation and also infrastructure planning activities. For example, last year in central China, Zhengzhou, where is a metropolis with more than 12 million populations. This city was hit by a heavy rainfall. The hourly rainfall in Zhengzhou is larger than 200 millimeters. The 3 days total rainfall is about 600 millimeters. What the meaning of this? Because climatologically, the annual mean rainfall is about 600. That means you got the annual rainfall only in 3 days. So you can imagine the disaster. After this kind of event, we are always asked by the policymakers at this question, can you make predictions? Actually, it's very difficult. What I shown here is the sources of extreme precipitation projection over the monsoon area. Here is the fraction of the contribution of different components. If we focus on the near term, for example, the future 10 years, you can find the uncertainty is mostly dominated by internal variability and also model uncertainty. So to increase the reliability of near-term projection, first, we need to consider initialization. This is called initialized decadal prediction. We need to consider the effect of ENSO, PDO, and AMO. Second, we need to improve the model performance. We need better models, such as convection permitting models, to well reproduce the extreme events. To make a summary, we have 4 points. First, climate change has made heat extremes or precipitation extremes in Asia more likely. Second, high occurrence probability is projected under future warming scenarios. And the third, limiting global warming to 1.5 instead of 2 degrees would reduce both area and the population exposure to dangerous extremes, such as once in 10-year or once in 20-year events. And finally, a reliable near-term prediction that focuses on the coming 10 years is very important, but it remains to be a challenge. That's all for my talk. Thank you.
Yeah. Thank you, Tianjun, for this excellent talk, which I think also nicely complemented the previous presentations. And sorry about the technical problems. I'm glad we could hear your presentation in whole, despite the interruption. We are now taking questions to the 3 speakers. Please put them in the Q&A box at the Zoom at the bottom. Maybe to kick off the discussion session, and while we still wait for more questions popping up, I can ask a question to all 3 speakers, and maybe also pick up the one on which Tianjun just finished his presentation, because I think it's quite interesting in the context also of this Lighthouse activity. So while there's a general expectation of entering uncharted territory in a warming world, so maybe it would be nice to hear your thoughts on what's the capacity, or to what extent we can make predictions beyond this trend, or what is missing, for example, to be able to predict the Northwest American heat wave, for example, really kicking in as such an event in 2021, but not already in 2020 or 2022, similar for the flooding event you just presented in for Changshu. Yeah, so you can maybe, Eric, do you want to go first? And
Sure, thank you very much. Yeah, very good question, and a very challenging one. So there's 2 aspects. So the one I've been mainly talking about is less a question of predictability. It's just pointing out the potential years ahead, right? That would allow preparedness, allow flood protection for heavy rainfall. It will prepare a public health plan for heat waves and so on. And there's the other question of predictability. And I think the second one we did actually for the heat wave case, which we have mostly been looking at, did actually a really good job. It wasn't us, it was mostly you, many of you basically working for in that field that did amazing job in some of these predicting these type of heat waves 10 days ahead in some cases. And a very good example is the UK, the 40 degrees this summer in the UK, right? And what we realized that forecasters are slightly nervous, basically, to communicate predictions that actually are record-breaking, right? Go beyond anything that people have experienced so far. I think that is a challenge, and in many cases actually became a reality. So I think a very good, this relates to one of the questions I also got in the chat or in the Q&A. How do we deal with that we potentially obviously also could give a false alarm? I think people in the UK case did actually a really good job. They pointed out this event appears in some of the realizations, but since we've never seen it, we need to basically sort of issue a watch and carefully look at that. And then the closer we came to the actual event, the higher the confidence. I think people, if we communicate this carefully, can understand that in some of the cases, yeah, the event will then not unfold, and in others it will. I think it's a challenge, but I think we can, and I think we also need to point out in the aftermath that thanks to prediction, I mean, we have been reducing many of the impacts of these type of events because they were so well forecasted.
Thank you. Maria or Tianjun, do you want to add something?
So Maria first.
Yes, well, I agree with Eric. I think communicate prediction is a key and a challenge, but also communicate the uncertainties, as Tianjun showed in the last figure. The communication of uncertainties is also very important to understand the predictions and to make good decisions.
So I also see one question listed in the OA box is from Leon. It's something related to this question. Do you think policymakers are ready to use probabilistic predictions? In the last part of my talk, after the flooding occurred last year in Zhengzhou of China, actually, we have been asked by policymakers many times, can you tell us with 5 or 10 years in advance? Because such kind of information is not available. You know, at the shorter time scales, we have weather forecast and the seasonal forecast. For the long term, we have projections. We can tell the society what will change in the coming 100 by the end of the century. However, we do not have solid projections for the coming 5 to 10 years. You know, each round of government is usually 5 years. 2 rounds is 10 years. So they need this kind of information for the infrastructure planning. However, currently there is no this kind of data set. I noticed in the talk given by Eric, you mentioned the Unseen project. It's an initialized prediction for the near future. Several days ago, WMO has released the United in Science of 2012. It partly released the near-term future projection. It's also probability prediction. I think such kind of information is crucial to policymakers. It's better than without prediction, you know. So I think it's also helpful. Actually, WMO has produced the leading center to promote such kind of prediction. Thank you.
Thank you, Joel. We have some minutes to answer 1 or 2 questions more, I think. We have a question to Maria Laura, that since precipitation observations are a challenge, could measured river stream flow be used as an integrated measure of total rainfall? What do you think?
Yes. Well, I think that it is an important observation, but it is not enough. in this context. It could be considered as an additional measure or a complementary measure, but measurement, but taking into account the nature of the deep convection of the deep convective storms of this region and the fast development of the system, direct measurement would be important too. And for instance, these kind of storms have a clear daily cycle, diurnal cycle with extreme events during the night. So early measurements are very important and are really scarce in the region. So stream flow, it's an additional measurement, but we need a more direct and at a time scale, a daily or hourly time scale measurements too.
Thank you. Okay, we have a last question to Professor Tianjian. Could you explain why rainfall depend on time scales?
Thanks. This is for the attribution of the observed extreme occurred in 2018 in Northwest China. Actually, for the RX1 day, is mainly dominated by greenhouse gases. For the 4-week-long persistent rainfall, is dominated by the aerosol because the mean state change has a large effect on this. You can guess 4 weeks persistent is nearly 1 month. It's similar to the climatological mean. In our analysis, we have checked it's mainly due to the aerosol. The aerosol has led to a weakened monsoon circulation. So the response of 4-week persistent rainfall is different to RX1 day. Thank you.
Marcus?
If we have time for a final question with a quick answer before there's another one for Professor Zhu. You said it is difficult to make a prediction for the Chengdu flood. Could you briefly describe the current advance of the prediction and what has been tried and what you have ideas to improve this prediction? All this in 2 sentences, please.
Thanks. At least for the flooding occurred in Zhengzhou last year, for the weather forecast, the China Meteorology Administration has issued alert many times. The prediction is accurate with 1 or 2 days lead time. However, the response of the society is not in time. The government also hope to know we can tell them the probability of such kind of event with at least 5 years in advance, because they need adjustment of the infrastructure. This kind of information is missing. What we have done now, as I mentioned, WMO is promote the near-term projection by building the leading center of near-term prediction. Each year, they release the forecast in the United Science, such as each year they have an issue. There are, in my memory, there are results of about 50 models available. Thank you.
Thank you.
Thank you. So the time for the webinar has come to an end, and we want to thank again all speakers. Thank you also for solving the technical issues so we could hear all presentations, and a round of applause to all our speakers, Erich, Maria Laura, and Tianjun, for their excellent presentations. Yeah, thank you also for all of you who are still online for attention and for the participation in the discussion by posing questions in the chat. Again, we intend to have these webinars about every 2 months, which means we plan the next event for November. And we are currently finalizing discussions about the next topic, and we'll send out the announcements soon. Thank you very much.